Good morning, all of you. Are you able to hear me? Am I audible? Hello. So I hope you would are able to see the quiz questions, etc., which had been uploaded yesterday. Today, okay. So Sanjeev, so many new people are there which couldn't interact earlier. So see now after so it's welcome you all to our sixth day. We have actually crossed about half of the journey, even more than half of the journey, because even we have in last 2 days bit hectic that we have covered the Sunday schedule actually also. So now see coming to the part see after discussing the basic image, thereafter image enhancement, we started with basically the histogram technique, and then we moved upon to the basically spatial filtering and then frequency domain filtering, and then thereafter we took up the morphology, etc. That where you want to basically modify the image, you alter the image, uh, dilation, erosion, etc. That we did. And before it, we actually, yes, very important part that image compression. In image compression, you do basically the different type of coding, run length, etc. etc. So that we have done it. So today, so now we are basically ready to start with new topic, image segmentation. All right. So what is your overall, any question, any weird difficulty? Are you feeling the connectivity between all the topics what we are dealing? Because it's all basically like a one thread. Just 2 minutes, the if someone has any questions. So that's the when we go proceed on the image segmentation. So everyone, I hope, would be with me. Before it, any question related with either content or with quiz, etc., whatever thing means you should feel free. So if you have any questions, see. No, okay, so no question. So then anyone from anyone, either of the one. Today we will have session from this 3 hour session, 10:30 to 1:30. Then thereafter 2:30 to 5:30. So that we will cover up that 2 hour basically of the 24th of the that December. Morning will be very right. So now see, and so now what we will see is the image segmentation. Regarding the image segmentation is a computer vision technique that basically partitions the digital image into a. So first we see into discrete groups of pixels image like pixel image to inform object detection related tasks. Remember, see whenever see for example, even when we are seeing any image, we not only see one image, but in one image we see many objects. Many objects lie there. So as our purpose of image processing and computer vision is there, that automation of seeing the different object in a one image should also be happen uh, at the machine level also. So what will be the next step to do it? It is basically the image segmentation, that you are able to identify the different objects, still right, lying in a one image. Now we are going towards the more even deep uh, at processing at the deeper level. Image segmentation technique, in image segmentation technique, it is basically the discontinuity. So how will you, where will you apply where discontinuity is there? Where similarity is there? See why these two things are together? See, because in discontinuity that where the you are able to know the boundary. Definitely when different objects are there, there will be a boundary mismatch or there will be a boundary distinction between the two objects. So based upon the discontinuity, you are able to find out basically the edge base. And how do we find out the edge base? Using the gradient, using the Gaussian. In the gradient, basically, what type of techniques we use? We use basically the Sobel, Robert, Previtt. In Gaussian, we use basically the Kenny's detection, Laplacian of Gaussian. In similarity part, you use basically the thresholding, you use basically clustering base, you use the reason base. Similarities is similar clusters are there. Similar on similarity base, you using the threshold, you find out the similarity. In the reason base, again you find out. So in the threshold base, you find out the global and local. See, threshold can be at the global level, local level. Reason based, reason growing, reason splitting and merging. So this is the one. See, so we will see. So now coming to the part thresholding based segmentation. So segment thresholding is an important technique for image segmentation and produce uniform reason based on the threshold value criteria T. Key parameter is the choice of that threshold value. If thresholding depends upon only grayscale value, it is known as global threshold, right? Yes, absolutely. See, all are basically the filtering that we have been discussed. Only they are under the different context only. If threshold, in case neighborhood properties is also taken into account, method is known as local thresholding. It depends upon see where are we want to see it. In case T depends upon pixel coordinates also, it is called as dynamic or adaptive thresholding. So what is important? See, what is this thresholding? It is basically a function of the spatial coordinates, gray level, some local property of the image. So when we are saying basically the thresholding based segmentation. So see, whenever we are seeing the image, we will able to make out the any meaning when we will see the images. So we see the original image here. In original image here, see for example, now we want to use a threshold. So if I put the low threshold, so when I'm putting the low threshold, so then what you will find out, so in this case, you will able to distinguish these many points. Initially, this was the picture. After putting the threshold, I am able to get the this N1 picture. If somebody say that the threshold is too high, so in that case, what would happen? In that case, basically, so these again, then these many number of points would be visible because all the points will come out here. There will be no role of the threshold, right? So this is, so what do you need to do? You need to put a optimum threshold, and remember, making optimum, it is basically a regular phenomenon, and it's a dynamic problem that how do you find out it. For example, see, this original image is there. In this original image, it is there. Uh, Here we are saying the dog is sleeping. If I put the threshold 50, so if I put threshold 50, see, we are able to see this figure, right? So see, what is important that, see, as for our natural vision, it is very, very easy to classify the object, to find out the different, to segregate the different object. But doing this part at automation level, it is a really very, very tricky job. That is, we are saying, so finding out this number is not only easy, but it is not always sufficient to find out the complete segmentation. That's why we have taken the different type of segmentation. Now we take the another case, for example, this is basically the source image. So for example, if you put the see global threshold, then you are able to see this figure. If you put the local threshold, then local threshold again, see, when it is basically based upon the neighborhood pixel values, etc. So then you are able to see this thing. So threshold-based segmentation, it is to, so what we are saying that the quality of threshold algorithm depends on the selection of suitable threshold, and the tool are there. Remember, please note it, segmentations are not a easy job. As like we had been, now we are moving to the more complex part of the image processing. Tool that helps to find out the threshold is histogram. So histogram is again becoming useful. So how does it? In types of histogram, you basically use a unimodal histogram, it is bimodal histogram, it is multimodal histogram. So what is the difference between this? The unimodal means only see one peak is there. In bimodal, you are saying it is basically two peaks are there. In multimodal, many peaks are there. Mode basically refers to the peak one. So what we are saying, it is basically, so how will we apply it? So that we will see. Suppose that an image is there, fxy, it is composed of the light objects on a dark background, right? And the stone figure is the histogram of the image. So, so what we are saying, it is single level thresholding. What we are saying that when we put the say single level threshold, the objects can be extracted by comparing pixel values with a threshold T. So see single level threshold, see it is easy to do, but where its limitation that we will see. If, for example, at any point x of y, if x of y is basically greater than t, it is called object, and it is less than t, it is called background. One of the simplest way to threshold is basically that we separate out the foreground or the object and the background. So somebody has put it in this way here in this figure. Multi-level thresholding. Multi-level thresholding, see now not only one object is there, many objects are there. So this is a C, you can see the example. Possible to extract objects that have a specific intensity range using multiple thresholds, right? So if T1 is, uh, see for example, so multi-level means more object. What we say here, range is there between T1 to T2, one object class. More than T2, it is another object class. Which class is there? Apart from it, it is less than T1, that you may say it is the background. So you can see here also from the, when you find out it here, for example, xy greater than T, you see, for example, what is this part? This part is our object, and this part is our background. See, for example, some ball is there, some red ball is there, which is lying in a your on a green grass. So how will you differentiate that? Basically, ball is the object and green grass is basically the one. Another thing, see, for example, green grass is there and two balls are there. One is basically the yellow ball, another is the red ball. Then in that case, your this example will hold. So here what you can see, here see this is the one, this is one part, another part, you know. So global thresholding. So global thresholding basically applies that in bimodal images, histogram have two distinct peaks separated by valley between them. As we have already seen it, see, are you able to see? This is basically these peaks are there, and what we call valley, this is basically the valley. See this region, this is valley. So see, till the part we are basically focusing upon the local threshold, but global threshold becomes important. So what is the global threshold? Global threshold, we are saying, is calculated to randomly select an initial threshold. When you randomly select then segment the image using two group of pixels, that is G1 and G2, then you determine basically mean of the pixels in G1 group that lie below T in basically histogram, then you determine mean of the pixels in G2 group that lie above T in the histogram. Initially we have selected it, then you determine the mean of basic. So mean that lie below T and that M2. Now new threshold basically T equal to M1 plus M2 upon 2. Repeat the step until the difference T is less than a predefined limit. So this is what we are saying. See, this is basically see initial local basically there we are selecting. So global it is what it is saying that how you can basically reach to the global. That is basically a way is there. That was initial and so this way here, for example, G1, G2, G3, whatever reasons are there on that basis, you are able to find out that the global. See, thereafter, see, people actually, it's a one, see, actually, segmentation exercise is all based upon the, see, contextual problem. In medical imaging, it becomes very, very difficult. For example, it's basically more black and white and for example, some tumor etc. is there. See how you can because the tumor itself basically lies in there. That's why it is not very easy to identify. Even see there, how do you mean they are really a very complex problem. So in also thresholding, so what does it say? So that's why people have come up always with a different type of techniques based upon their content. So also method is basically applied to the images which are bimodal, which means the image is having two peaks in the histogram. So also method is an automatic threshold selection technique used image segmentation. Find the best global threshold that separates the image into two classes. Foreground and background does not set threshold randomly like global threshold technique. Again, see all these techniques are to find out the global threshold. Unlike see we have selected earlier, here you don't need to choose it. What do you only the requirement here that there should be a two peaks here, right? So this peak is there, so this is there, so then it has been basically calculated. Which are the peaks that we can find out it here? This is one peak, another peak. So Parvesh is saying Let me read it. Pravesh is saying, first we find the histogram, and on that basis we will decide which thresholding to use. Right? We and on that basis we will decide which thresholding to use. See, histogram definitely when you are using here, uh, as we are basically using the finding out the histogram, then based upon the shape, then we are able to identify. Yes. Because the threshold is not a easy job to find out. So yes, we may start with this type of technique. So what is mathematics here? Mathematics we can see here. See, for example, this is the case here. So here see histogram, the perfect histogram is there. The frequency is given on the this y-axis. On the x-axis it is gray level. Can you tell the how many bits are there? How many bits are there to represent the all things are interrelated. That's why we are always emphasize upon basics. How many bits are there in here in this diagram? 8. Sandeep is saying 8. So you see what we are saying here. See, 8 is everyone saying it is 8. See, please note it here. See, bit is basically you see what is the highest number? What is the highest gray level? What is the highest gray level here? See, 70 is actually the highest one, but it is actually here 64 here, right? So in the 64, what we are saying, it is 2 raised to the power, yes, 2 raised to the power 6. That is there. Remember, gray level will always be in basically the 2 raised to the power only. Why? Because it's basically based upon the number of the bits only. So how do we do this calculation? So we first check out this calculation here for pixel value 3. So here basically you need to calculate the weight here. So what do first we calculate the for pixel value 3, and then you calculate basically the mean value, and then you basically the variance, and thereafter the within class variance this value is given also this thresholding. Then for the multiple thresholding, see there was basically the one threshold, and the multiple thresholding it is an extension of simple global thresholding. Instead of using one threshold to separate the image into foreground, background, multiple thresholding uses two or more threshold to divide the image into multiple regions. So if it so that's why it has been given here, that we have already read it. Multiple thresholding, see for example this original image is there, see bi-level thresholding. It is you are able to here you are able to identify in one threshold is there, but multi-level you are able to in this is the figure. See, we have set the different thresholds, but it is another thing that we are in what context we are selecting the threshold. Because once we need to demarcate the as different objects if we are also clear that for which objects we are setting it. For example, in this image, even we know that it is a multiple level thresholding, but we can't say that for what purpose it has been used. Now coming to the part adaptive thresholding. Adaptive thresholding is basically that where the threshold value changes across the image, right? Instead of using a single global threshold. So what we are saying here, as we told it, that it is basically based upon the pixel value, local pixel value. Here, see threshold value changes across the image. This is used when lighting is uneven across the image. Techniques basically to apply thresholding algorithm. Here you divide the image into many overlapping sub-images. You split the image into many sub-regions. So what do you do here? You divide the image into many overlapping sub-images. So how does it happen? So you take basically a window. You take a window. Again, it's like a mask concept, but so here you take a 15 by 15 and 31 by 31 pixel across the image. Each window overlaps the previous one. The threshold is computed for every window. You calculate basically the local mean variance Gaussian weight mean. This gives a smooth pixel by pixel adaptive threshold, right? Why use then we overlapping windows? Overlap basically prevents sharp block boundaries that produce the smooth transitions. It handles uneven illumination very well. Here you split the image into many non-overlapping subregions. The image is basically divided into blocks. Each block gets one threshold value. This is sometimes called block-wise thresholding. We also use basically the subregions. It is faster than so. Here basically we are using overlapping sub-images. Here you are using non-overlapping. See, but remember, choice is definitely the non-overlapping, but sometimes it's more possible. So here what we are saying that it is into blocks, and each block gets one threshold, and this is sometimes called block-wise thresholding. See, why do we use basically sub-region that is faster than overlapping window? It is good when lightning varies between different regions. It is suitable for the larger images. Remember, when larger image is there, then only these sub blocks are there which can work. Another is basically the region growing segmentation. There is a procedure that group pixels or sub-region into larger regions. Logic behind region growing is the principle of similarity. The region basically, for example, our geographical maps, etc., are there. There we basically use it. So here principle of similarity, what does it state? That a region is coherent if all the pixels of that region are homogeneous. So how do you are basically find out on what basis we are finding out that homogeneity? That may be basically the gray level, that may be the color, that may be the texture, that may be the shape, model. Again, the segmentation very much depends upon the objective, what you are going to achieve it. So that is basically the here that there is a region growing segmentation. We have what are the major steps of region growing algorithm? That is basically selection of the initial seed. Thereafter, you take the seed growing criteria and then termination of the segmentation process. Region, yes, it is basically see definitely is actually see in medical session we will, but yes, see I am yes very much part is there, but what I will suggest you that next week we will have the many medical sessions. There you will see these things. And yes, it is you. So, so how do we do it here? So first, basically, we select out the seed point S1 and S2, right? in S1 and S2, basically S1 value is 9 and S2 value is 1. So thereafter you take out this threshold. Yes, seed point basically what you have taken, you have selected, you have taken it basically randomly. Then the in between we take out the threshold. That threshold is basically it is take the T and then thereafter T here, then it is basically the seed point is basically the initial point. Initial point what you are taking. So see initially basically we have taken these see initially we have selected these points. Definitely see between seed point it should mean basically with the maximum see distance actually. Maximum distance is there so that see in between only then we can put out the threshold. If you put the two seed points nearby, they are almost nearby, it is very, very difficult to set the threshold. So what we are saying here, for a given image, we show the results of region growing algorithm. So what is here in this example, it is so what is our purpose here? See, so for example, we are able to basically differentiate the different points which are basically less than 4 and which are greater than 4. So for example, when we are taking basically fxy, when you have taken this point -9, this is greater than 4. When your fxy equal to basically which value, when it is taking 5, then you're taking 6, 7, 8, 9. In all those cases, when you take this value, the mod is there. Mod is basically less than 4. Wherever this mod is there, what we call it, this is basically, this is the A region. Then you take the next seed, and in this case, what you say that basically fxy minus this one, this is basically mod or less than 4. When this is mod or less than 4, and see this value is basically 1. So what we say that what are the values basically which fulfill this criteria? So here it will be 0, 1, 2, 3, 4, 5. So that will be the reason. So in this way, see, after selecting the seeds and then we have using that condition, we are able to find out the segment. So how it has been segmented so that you can see. This is one segment here and this is another segment. That's how you are basically selecting the region. Thereafter we come basically toward the region is split and merge segmentation. Split and merge segmentation is a region based on the quaternary structure. It segments an image by recursively splitting into smaller regions and then merging regions that are similar. It is basically stated in the two phase, basically phase 1 and phase 2. Split and continuous subdivision process until some stopping criteria is fulfilled. Often it is stored when no further splitting possible. In phase 2, basically merge adjacent regions if the regions share any common criteria. Stop the process when no further merging is possible. So here see more example are there. So we will actually, what I'm planning that we can do it uh, later in our problem session so that we can clustering based segmentation. So you see clustering based segmentation. In clustering based segmentation is basically again you make the different clusters actually. Again for each cluster there will be a separate threshold. So what we are saying here that let consider an what is basically clustering? Clustering is a method to divide a set of data into a specific number of groups. It is basically one of the popular k-means clustering. K-means clustering is a partition as a collection of data into a k number group of data. So for example, we can consider an image with a resolution of xy and the image has to be clustered into k number of cluster and p with the input pixel to be clustered and ck with the cluster center. The algorithm for k-means clustering is given as this one. What we are doing initially, we see the number of cluster for each pixel. You calculate the Euclidean distance between the center and each pixel. Then you assign all possibles to the nearest center based on distance g. After all pixels have been assigned, then recalculate new position of the center using that given below. You repeat this process until it satisfies the tolerance or error value. Then you reshape the cluster pixels into an image. See, it is, but major problems are also there that it depends upon arbitrary selection of initial centroid. So there is been shown here this flow chart that number of clusters, you find out centroid, distance object, and then group it. So this is how it's working as been shown. What I'm thinking that we can take up this example in our afternoon session so that we can cover the maximum concept in our this part. So now coming to the most important part actually of the image processing in especially in context of the AI, artificial intelligence, machine learning and the deep learning. So what is basically the feature extraction? The feature extraction, if you really see for example, or as a human, if you ask me that can you differentiate between bike and a scooter? See, for us, it is very, very easy. Even we don't, and even we remain accurate 100% of the time. Even you ask any small child of the weather of 5, 6 years who are able to, so they are also able to identify and without any error. Remember how they are doing it, how they are doing it, that this is scooty and this is bike. So remember this thing, they are, we assume it that they are basically using the distinguishing feature, key feature. What is this feature? Feature almost we say that is basically the characteristic, right? This is such an important word, such a very basic word that it comes everywhere. What do you mean by feature extraction? It is characteristic. So this is characteristic. So how do you extract that characteristic? Remember, again, it depends upon the context, and it is that is the beauty that we will see. Feature extraction is process computer vision and data analysis that involves identifying and extracting. See, not only you need to identify, but also you need to extract out. It means you should put up in such a way that it can come out. Mathematically, when we are putting the thing so that that value can be separated out. That is the key thing. Feature extraction aims to reduce data complexity while retaining as much as relevant information as possible. So this helps to improve the performance and efficiency of machine learning algorithm. As I told you, see, as soon as you begin to use machine learning, see, this is the key thing. That's why we are saying that feature extraction is the most important topic when we are basically talking about the image processing with machine learning and deep learning. So what is has been shown here in this example, it is shown, for example, the bike is there. So if you feed it to any feature extraction algorithm, it will break into different images. So how, so remember tire is there, see this part is there. Now what is our purpose? Our purpose is there that we should able to identify such a feature that it may be unique one to this bike. So even see, you would have seen this type of problem that, for example, this to check out that the this control of the robots. Many times this automatic problem is coming. You identify the bike, you identify the cross lane, etc., etc. Again, see, they gives a different problem. Even see the normal human being, many times we are not able to do it correctly. But again, see, they are asking the same type of task. So in feature extraction, the process basically to express the texture of an image with value. When we, for example, see if we are able to express the texture with value, it can be used as feature extraction. So if some surface is there, that is basically the plane one, so it means it has a this is 5.88. If something is basically a little bit harder one, it is 9.74. Then in the other case, it is basically bit more, uh, even say it is even it's a what do we say texture is like a pattern, right? More uneven type of thing. That is 12.78. Here it is even more uneven. It is 21.54. Here it has been increased. It is 23.85. So there it is 21.7. It is 26.46. Here 38.56. Where do you use it? See, for example, some stone, etc., different surface, etc. There we find out these basically where we use the texture. Texture with different roughness quantified with the value of standard deviation. Not only we use this value, but also standard deviation is also allowed. So basically the process to express the texture of an image with numbers is known as feature extraction. So what we are saying here that basically the first order statistics is used, that is GLCM, that is basically the mean, another mean Gabor filter based feature, local binary patterns, that is gradient based feature. So first order statistics is why we are saying first order statistics. So for example, when we take the data, see when we take the many values, so then we are able to, this is one of the simplest way, first order statistic. For example, if some value is given, see, for example, when we are finding out the different tile or different type of stone, see, we can never ever say that it will only see with that texture only will be a that type of a stone. It's very difficult to say. So what do we use in that type of cases? We basically use a mean with a standard deviation. We also use a maximum problem, minimum problem, then range, then skewness, kurtosis. For that, see for how much range is there, right? Second order stress. In second order stress, basically texture are basically pixel pair relationship. It is most widely used. It is gray level co-occurrence matrices. It is Here, gray level co-occurrence matrix calculates the joint probability of two pixels separated by distance d and along a given direction theta, having co-occurring values I and j. Has been. So it has been shown here. So we will 14 textual measure defined by this one here. So again, see these different features. See, because see what we are going to do whenever we are going to these automatic things, what we can do, we can basically calculate the mathematical parameter. Angular second movement, basically, is what we are saying. This is so. What is basically the first feature? Angular second movement is energy or the uniformity. It means that the number of repeated pixel pairs. The energy is expected high if the occurrence of repeated pixel pairs are high. What is this PIJ value? That is basically the normalized co-occurrence metric. Gray level co-occurrence matrix. Here it returns the measure of local intensity, contrast of an image, how different the gray values in the pixel pair are. So there we are showing the contrast is expected low if the gray levels of each pixel pair are similar. Definitely we are not going to get the different contrast when it is the group of pixels are similar. So now we come to the part C, local binary pattern. Local binary pattern C is basically texture descriptor that is used in image processing. Convert the local neighborhood of each pixel into a binary number based on intensity comparison. So why Peter is saying local binary? Because finally then it converts into a binary number. LBP basically uses facial expression, facial recognition, facial expression recognition, texture classification, object detection. So how it has been used, basically the most common approach is that each window you take a 3 by 3 window in the image process to extract an LBP code. The processing involves basically thresholding the center pixel of that window with its surrounding pixels using the window mean, window median, or the actual pixel. So how do you find out this? Basically is a locus binary pattern. So here say 3 by 3 window is given shown here. So we calculated basically summation from 0 to 1 basically where S, I n minus I c and what is so what is I n? I n is basically the neighboring pixel and I c is basically the center pixel. What we are saying? We are saying that you need to calculate the LVP in this one. So value is given here. Over here when we take the value. So what we are saying, so only thing is remain here that to define the SZ. SZ is defined as 1 when Z is greater than 0 and it is 0 when Z is less than 0. Because finally we have to find out a binary pattern, right? So that will be showing here. So 5 when we are taking neighboring pixel, it is 5 and central pixel is 2. So 5 minus 2 and then n is 0. So we will get here s equal to s3 into 1 and it is equal to 3. In the same way, when we are saying here that the local binary pattern, and let's see the image is there, that part is. So what will we do? We'll basically multiply it, and then we will add up. uh, So here it has been shown here, this figure. So what it has been shown, this is really 2 raised to the power, it is 7, it is 2 raised to the power basically 2, 2 raised to the power, it is 6, 2 raised to the power 5, 2 raised to the power 4, 3, 2, 1, 0. All these values are. So input image is here. This is basically LVP image, and here also we are basically drawing the LVP histogram. Another is basically local ternary pattern. So what do we do in this local ternary pattern? In this local ternary pattern, so again, see, we have taken this as a different mask and we are calculating value. This is basically histogram of oriented gradient. These are what does basically histogram oriented gradient do? Histogram oriented, see what is important here. See, as from the name itself, it is histogram, but here gradients are calculated. That in which direction your orientations are there. So that is basically calculated. So, for example, some number 8 is there. This number 8 is written, and then is trying to classify that thing. So here we take up a one break here so that we can come up with it. Now am I audible? Hello. Yes, thank you. So see, now coming to the, we'll take up the numerical of these problems, see whatever we have in the afternoon, that mathematical part, so that see we can cover our content, finish it by today. See now coming the histogram oriented gradient. The earlier see the, as we have realized that the most beautiful thing of the histogram is that it is very easy to apply. Whenever you see what you are doing, see whatever thing is there, you just need to only count that thing. So when this concept was initially applied in the image enhancement, later on see it was applied as feature extraction. See both the things are different. When you are taking as feature extraction, it is altogether a, we say there's a we say the most advanced processing about the image. So before again we see it. See, for example, if I want to differentiate the different digit. For example, what you are seeing here that this number is 8. So when this number is 8, see what we are seeing that the basically white part is highlighted here, and so how it is highlighted, if you see here, see if you, so how does the computer see it? You are able to see that in this curve line. See this curve line, whatever it is going here, and if you see here, see this is basically going here. All these values are white, and here they are basically 250. They are more than 240. They are continuously going. So what we are saying that so pixel value for white, so this way we are able to notice it. Another thing, it has become very, very successful. This is to now Fourier gradient. See now, for example, color image is there. So how computer see the color image? And color image, see, it will be a different, it will be a different scale, RGB, etc. Remember, it is in the addition to the grayscale. So there also we may observe the basically the histogram of the oriented gradient. What do you mean by this oriented gradient? Oriented means basically the angle is also there. There at what angle, this angle information apart from that pixel intensity. Earlier we had been only dealing with the histogram of pixel intensity. This time we are also including the orientation, histogram of orientation. For degree, how many orientations are there? At 40 degree, at 90 degree, how many vertical lines are there? How many these different orientations are there? That histogram is also noted down. Even see, I tell you that when I began to basically apply the image processing, I really initially record means learn the things from this thing, histogram oriented gradient. When I applied on my thesis work of the basically facial expression recognition, it was because what is the thing? It is very easy to apply, and it is effective also. So remember both these two talks are there. But what is important that with the oriented gradient, you are able to also distinguish that which one dog mouth is open. That also it can be calculated. So variations in background color and expression that basically lead to noise. But what is the problem that whenever you taking the colors etc., it becomes computationally expensive. Then you need a systematic approach to capture crucial and discard redundant information. So HUG or histogram oriented gradient is proved very well here. So how do we calculate it? See, again, see what will be spatial here, that this orientation part, how this orientation part has been taken care, this angle part. So where this we will see it. What we are showing here. So first, basically, they are pre-processing. What do you mean? What do you do in pre-processing? Pre-processing means basically we all bring all the images at same level, same size, same color. Either it is a gray scale or it is a red, blue, yellow, whatever it is there. Then you calculate the gradient of the image. This is important. You calculate the gradient of the image. Then you calculate the histogram of gradients. Remember, it is histogram not of intensity but of the gradients. In which cell? In 8 by 8 cell. You take any cell here. You take blocks basically here. There you calculate the histogram and thereafter you do the block normalization and then you form the. So it has been shown here. For example, some block has been taken here. After this block, see here, this different gradients are plotted on the x-axis. Here it is count is there. And then after, then we calculate the histogram of gradient. And then after taking this 8 by 8 cell across the image. So for example, if it's my image is basically 64 by 64. So it means 8 and 8. So my feature vector will be of the 16 length. Right. So in this way, we are able to form a HOG feature vector. Why this feature vector? Feature vector means it basically tells its dimension is either it would be either 50 by 1. This is basically the line. That's why we call it the feature vector. It is. Then what you do thereafter, you calculate gradient and orientation, build histogram, then you normalize it, and then so what do you do? Now we check out, see how does the things work here. What we say that the plot images, pixel orientations, and gradients on an histogram. So for example, where do you see that this gradient? You are able to see here. You are able to see this angle, this angle. This is vertical. This is some angle. This is some angle. Here it is some angle. What do? You plot image, pixel orientation, gradients on an histogram. Histogram that becomes a. So it simplifies representation of image. You see why this orientation? Remember, if you recall the earlier problem, see now not only that the histogram has one basic problem that even the two different animals are there, but with the histogram of pixel intensity, it may be the problem. So that's why we have sorted out that problem and we have moved in another way, because feature vector is even a more we say more advanced task, that where you need to take the decision regarding some. This is original image so that you are seeing here. So now here you see this is some angle, here this is some angle, here this angle is there. So what do we do in pre-processing? We basically resize it with 40 by 80, then you take it 32 by 64. Why somebody may ask 32 by 64? Because when you are taking a block of 8 by 8 cell or 4 by 4, you will make a complete block. Every cell will be covered without covering it twice. That's why we are taking basically exact multiple in this way. So that's why it has been shown, it has been suggested here that image size is basically 64 by 128 and cell size 8 by 8 and 16 by 16. It is there. because it's a complete multiple of. So, for example, so now see when this dog is there, what you are seeing here that it has been divided into the number of the blocks, right? When it is divided into the number of the blocks, so hereafter it has been shown here, and as we are, so what is this? This is basically 4 by 4 block. You can take either, see, this is HOG cell size 4 by 4. When you are taking basically 4 by 4, so what is this value? This is basically 121. This is 10, 78, 96. Can you tell what is this uh, value here? Remember this. Can you tell what is this value? Don't we have to preserve the aspect ratio? See, aspect ratio, we are not bothered about it because see, here we are discussing the things for basically identifying the feature for distinguishing it. We are not trying to rewrite the image or something. That's we are not bothered about it. So aspect ratio, etc., really doesn't matter. But and even when you do the image resize, the overall object remains there. Can you tell what is this value? What is this pixel value? What does this indicate? 11.43. No, no. See, what is this value? 1085. Okay. No, see, that is fine, but what is this thing? This 152, this is 64, this is 125. Are you able to understand what is this value? 200, this is 214. It is see, no, it's a 10 value. It can't be a 10 value because it can't be 56, etc. 214. If you really see, these are basically actually the gradient value. The gradient, these angles are there, right? These are basically the different angles are there. For example, it has been shown here, this phi. This orientation is there. That has been shown here. See, for example, see here, if you see this quantity, this is 89, this is 78, this is 64, this is 56. So these are basically your gradient. This is basically the angle, right? Because please be clear that here we are not using the pixel intensity because it is a colored image. How can you take any? It is not the grayscale image. That's why we are taking it here. So it has been shown here. So that's why it has been calculated. But we call it as the bin also sometimes. Total gradient magnitude is this one, orientation is this one. So thereafter we calculate the magnitude and in this way we complete this chart here. What we are saying here that the gradients or highlighted blocks. For example, see here it has been. So what do? You take basically the different cells, and from the different cells you find out, take the HOG, and then HOG, and then you find out a overall feature vector, right? So here the gradients are shown. So here we see normalized vector for all these blocks having this much, and image feature descriptor actually this much size is. So it has been shown here. For example, even in my case, I used it that whether for the facial expressions, in facial expression, I need to know that whether the lips are open or not, whether the eyes are open or not, whether the eyes are broadened or not. So these type of information are very well captured by the orientations. If you see here, see this blue this one, there actually are the arrows which are showing basically the gradient, which are showing basically the angle. See what type of angle it is there. So you can see here this, see here this type of angle, here this type of angle, this type of angle. So what it has been shown here, so if you are taking it even at a, see for example, if you take the big cell size, for example, you are taking 64 by 64, then it becomes more large and it will overlap. So again, see, you have the choice to take the different sizes. The good thing is that if you take the size that smaller, the feature vector will be much more larger. But definitely accuracy goes very high. But while the size is actually very large, then the accuracy is not likely to come as like in the smaller. So this is the histogram gradient. Now we come to basically the part of the wavelet transform. Wavelet transform, as we have basically gone through the Fourier transform. Fourier is basically 2D Fourier transform. Yesterday there we saw basically the frequency based filtering where we, for example, what did we refer there? We refer, if you recall, see if my image is G X or Y. See, that's why basically we considered it in the Fourier transform that Gxy lead to the capital GUV that. But here the problem is that you are able to know that in Fourier transform, see what is the thing that which frequency you know the which frequencies are present that you are able to know by the Fourier transform, but the occurrence of frequency, what we are saying, see, but that the occurrence actually overall we know the frequencies, but at certain point of time, we will not able to tell that which frequency is present. At this moment, between this time band, it is very difficult to tell. That is the problem. So to address out this problem, the wavelet transform is coming to picture. What does the wavelet transform say? It refers to the analysis of mathematical function, physical signal, for time series of economic or environmental data with respect to time. As it has been shown here, that the Fourier transform provides frequency information of signal that represents frequencies and their magnitude. It does not tell us that when in time the frequency exists. As we have been saying here, it is exactly the same line. The transform is therefore ideally for the stationary signal. Lacks capability to provide frequency information for localized signal region and time. So how can we understand it? When frequency domain, it refers to the analysis of mathematical functions or signals with respect to frequency rather than time. I know the number of people within each segment at the given time, but where each one is sitting and their height, that is not known. So that's we are aware that yes, in this house, so many people live, but at particular time, how many people are present to that type of analogy has been told to read the wavelength transform. So in this part, the short time Fourier transform. So short time Fourier transform was developed to overcome the poor time resolution of the Fourier transform. It gives us a time frequency representation of the signal. With STFT, we can assume some portion of the non-stationary signal is stationary. We assume some portion. We then take a Fourier transform each stationary portion along the signal and add them up. So when we after dividing into the some portions of station portion, then we take out the Fourier transform and then add them. So this has been shown the wavelet transform. So what you are able to see here. So we take a window function of fixed length L and move it along the signal from start to end and take a Fourier transform at each stationary section. So this is the formula. This is the formula of the Fourier transform as we are told it. So what is actually happening in the Fourier transform? We are basically representing our signal into the form of complex exponential. What is happening in the short-term Fourier transform? See, not only we are taking it in the time domain, but also we take it basically the shifted version. And it will work for the. So what is this? This is also called as the window also. There are limitations. What are the limitations? That window function is finite, so frequency resolution decreases. Fixed length of the window means time and frequency is fixed for the entire length of the signal. We can't know what frequencies exist at what time instance, but we can know what frequency bands exist at what time interval. So it has been shown here that time frequency analysis that comprises both techniques that study a signal in both time domain and simultaneously using time frequency representation. What it has been showing here that it is basically narrow window equal to the good time resolution, poor frequency resolution. If you take a wide window, then it is poor time resolution, it is a good frequency resolution. So you can't achieve both the things together. So now we see the wavelet transform, which results in analyzing a signal into different frequencies at different resolution. Good time resolution and poor frequency resolution at higher frequency. Good frequency resolution and poor time resolution at low frequency. So what does the basically wavelet transform look like? See, if you see at this function, this is the one, this is f of tau of S is basically 1 upon mod of S is integrating Ft psi t minus tau upon it. This is what is with the wavelet function. Now we come basically to the FFT versus wavelets. In wavelets, basically, we can compare that father and a mother wavelet. So how do we represent it? You will represent it here in, so this is the way when you are going to represent it. And how you are going to represent basically the FFT. In FFT, see, it has been basically the in this way, cos. So it has been further simplified, and you can. So here, an important aspect of biomedical signals is the information of interest, often a combination of phenomena that are transient and diffuse. So, what we want to say that whenever, for example, then automatically something has gone high. So that is basically a critical condition that we want to really interested in. Such phenomena are characterized by the local phenomena information that exists in the time domain, frequency domain, or both. So what we are saying is to analyze the signals, we need a one method which can capture the event that prevent these extremes by localizing information from time domain frequency. So one of the heavily utilized time frequencies is the wavelet transform and the generalization of wavelet packet transform. So this is, you have seen it, time frequency. So this is the keyword. Wavelet basically divide the signal of interest to different frequency component. Each component will be studied at resolution matched to its scale. So this is basically the wavelet basically look like it's basically a finite wave, and so that is basically the more skewed one, that is basically the more broad one. So in wavelet transform, you can change the width of the wavelet and its central frequency as we may move across our signal by changing it. This is called basically scaling. So if we shrunk it, it is better at resolving high frequency component with good time resolution. Also, what is the common change here? The common change here is basically this one. This base is there. Earlier it was a complex exponential base. Now this is the base. And what is this thing that you need to find out? What we are saying, the wavelet family here. See, in the wavelet family, it's simply wavelets as gender. Their father wavelets also scaling function in a mother wavelet. The father wavelet itself is constructed from a mother wavelet by dilating the mother wavelet. Dilating the mother wavelet produces a low frequency wavelet that maps onto a lower frequency region of the signal. On the other hand, compressing the mother wavelet produces a high frequency wavelet that maps onto a high frequency range of the signal. What has been considered that when you are taking basically the low frequency range of the signal, then you can really compress and squeeze the given data. So here what we are saying, so once we are decomposing the signal, before some signal is there, it has been decomposed at a different level. So we can, because finally what you are seeing the signal basically some of the individual signal. So here the EEG band is also shown, and EEG bands is delta, theta, alpha, gamma. They are shown. If you are aware about the person when you are sleeping, then it is basically delta. Theta is basically a bit active. Alpha is when you are really preparing for examination, etc. So the multi-channel EEG pro. See, so this is basically the mask where you can see this mask here. And there are 128 EEG channel with 6 feature channels. Total number of feature here, see, it will be 128 channel, and each channel has basically 6 features. So it will be 768. So now we are seeing the overall block diagram of wavelet transform, basically. So this image is there. This image basically after passing through the low pass, and then upper one the high pass. Then again we have downsample it again. Then we have taken the low pass, high pass, and in the another image when you have taken directly and doing the basically high pass filter. Thereafter we did the low pass, and then after it is a high pass on. So this is basically the wavelet. Basically, this different levels are there. Here, if you see the original image, it is the most likely to nearby this one, LL1. So even the LL2 is more closer on. So they are basically created, and when they are created, in this case, so we are able to calculate the different versions of the image. So this is basically the original image is there. In the original image, so in original image, first you are basically doing the horizontal separation, then you do the vertical separation. So application of wavelet transform, if you really see it here, it is applied at the low pass filter, it is applied at the high pass filter, and then you basically downsample it, and then you again pass it to the low pass filter. And thereafter you basically get the two reduction, and you also use basically the two high pass filter and there. What is this application? So this in this application of wavelet transform, so here basically you are going to read the different type of images with almost nearby accuracy. So now thereafter we also introduce some one more algorithm that is again for the feature extraction. There is a scale invariant feature transform. Here we basically to detect and describe local features in image. So what do we do here? It is basically use for feature detection, object recognition, and image matching. So what is the advantage? The advantage clear industrial, uh, clear detect instead of invariant key point and generate robust descriptor that can be used to measure those key points across different images. This algorithm basically this algorithm basically achieves a scale invariance. It can detect the same feature regardless of the image scale. Additionally, it is rotation invariant, which means the key point will remain consistent even if the image is red. So it's a 2 hour. See, we just change the session and we'll be back in 5 minutes.